first chap we've got up today is Alastair Black. So Alastair's in the Shrewsbury Water Forum. Alastair is an independent I can't say it, nothing's coming out. I must slow down. Alastair is an independent hydrogeologist at Groundwater Science here in Shrewsbury, and it's a surface and groundwater modelling consultancy. Alastair's also undertaking a PhD at Newcastle University, so we'll be able to call him a doctor soon. Today, yeah, I think so. Alastair is going to have a quick look at the geology of Shropshire, some of the groundwater models, and also the Shropshire abstraction scheme. So over to you, Alastair.
Okay, great. Thank you very much. So in the UK, we've got a rather unusual and wonderful thing that the Environment Agency has developed groundwater models which span all aquifers in England, and in our case that's the Permo-Triassic sandstone is the aquifer for northern Shropshire. So these groundwater models are primarily used for the regulation of groundwater wells and also for impact assessment. So the reason we're introducing them here as part of this event is that they contain a very large volume of data, but more than just the volume of data they contain, there's a lot of understanding that has been brought in there as well. So in the development of these models, there's a large collection of local experts which come together to try to pull those data sets into some kind of a coherent whole, give some sort of explanation for them, building a conceptual model around that. So in Shropshire, this model, in inverted commas, actually comprises 3 parts. So we've got, first of all, a geological model, so a 3D model of the geological subsurface. And that image on the right-hand side is a picture of the most recently developed model for Shropshire. So the area is covering Knockin, Albury, Shrewsbury, Wem, Market Drayton, here roughly moving west-east. Across that, I can't go into the detail of the image, but as was said previously, we've got a very, very diverse and complicated geological setting where we live. So geology model first. In addition, the next part is this river and shallow zone model. So basically how water flows across the surface, how it infiltrates into the ground, the shallow part. And then finally, we've got the groundwater model. So once it's infiltrated into the ground, deeper flow pathways through that geology. So all 3 of those are linked, and they make a singular system for water movement in our county, or at least this corner of it. And it represents the full water balance. We can move on to the next slide, thank you. So a model is a repository for everything that we know about the system. It's deliberately set up as a framework to suck up all the data sets that we have that are relevant to how water flows. And once we've collected all that data together into this framework, then it can be used to start making predictions on what would happen if climate's changing or if human behaviour in groundwater abstraction is changing. So it's moving from becoming a coffee table book of data sets into something that's more of a predictive tool, a management tool, where we can run scenarios and do, well, what if situations. And for the groundwater model, the primary focus of that is how will wells reduce river flows and how will wells reduce groundwater levels. River flows, effectively the rivers are connected to the groundwater system. So if we take water from the groundwater, then effectively that is at the expense of the rivers. So what's in this repository? Well, it's going to list out some of the data sets, but I'm not going to do because Steve's wonderful talk has already gone through so many of those. Effectively, pretty much everything that Steve presented earlier on today gets subsumed into these models, and there's a collection of other data sets as well, in particular in relation to geology, boreholes, seismic data, structural information, faulting information, all gets pulled in as well. And there's also aquifer properties, so the properties which govern how easily water can flow through the rock mass towards wells, towards rivers. And it's been previously mentioned, the Shropshire Groundwater Scheme. In our county, I think we host what I believe is the biggest groundwater extraction scheme to support river flows. So that's, again, a wonderful operation by the Environment Agency where they effectively protect the river at times of dry periods or low flows, where they abstract water from the ground and discharge it into the river to maintain appropriate flows. Can move on to the next, thank you. Don't worry about the detail in this slide. One of the questions earlier was talking about digital twins. Was saying earlier that there's a collection of data that goes into these models. Well, that's what we know about the system, but what about what we don't know? Everything in between those data sets. Well, there's in making these digital twins, effectively have to try to estimate what happens in the areas that we don't know. And we calibrate the groundwater model to observed known groundwater levels at observation boreholes, and adjust the uncertain properties to try to honour that reality in places that we do know, and then get a bit of analogous understanding for the areas that we might not be as confident. And that's what we're seeing in these images. It's trying to match the green line, the simulated line, to the blue dots, which is the observed. So that's groundwater level time series over space. And if we can move on to the next slide. We do the exact same thing for river levels, so or river flows. So again, rivers are linked to groundwater, so we get a vast amount of information understanding from that. I can move to the next. So once we have our calibrated model, then we can start to look at how water flows. This is a surface water link to that model. So the image on the left-hand side is the total flow passing down the Severn and the Tern here. So the bluer, the higher the flow rate. And on the right-hand side, we can look at the interaction. So red is water flowing from the river, draining into the ground, and blue is the groundwater entering up into the river. And we've gone to the next slide, coming to the end. We can look at, so the previous was surface water flows. These are groundwater levels. The one on the left, we've got a grey model run, which is without a particular well of interest, and the green line is groundwater levels with a well. So we can try to understand how it changes levels over time. And the plot on the right-hand side, what are we looking at here? This is an estimate of how groundwater levels have been reduced on account of pumping. So the model helps to manage the groundwater resource, the impacts that pumping may have, and the river system, especially in times of low flow, better. But more than that, it's an excellent collection of data and understanding that could be useful for other studies. So move on to the final slide, which is just what you've seen before. And these models, they're administered by the Environment Agency, contain a lot of data and hopefully could be useful to some. Thank you.
Super, thank you ever so much, Alastair. Great visuals in a very short time. Thank you. So we'll take questions at the end. Okay, thank you. Next, we have got Mike Piotrowski from GeoSmart. Mike has worked at GeoSmart as a principal hydrologist for the last 5 years. He started his career with the EA, the Environment Agency's modelling and hydrology team, over a decade ago, and he's worked in water and flood risk management sector ever since. Generally, he, on a day-to-day, reviewing modelling studies and assessments, but mainly for development purposes. And today, Mike will provide an insight into the surface water model of Shropshire flood risk management and sustainable urban drainage systems. So over to you, Mike.
Thank you very much, Juliana. So yeah, firstly, I'd like to say I'm really pleased to be here to talk to you today about surface water and modelling across Shropshire. So I recently moved up from Reading to Shropshire, so I'm sort of finding out a lot of stuff along the way. But yeah, due to my background in modelling flood risk, have some good insight. So can I have the next slide, please, Kat? First of all, let's talk about what surface water is in its various forms. So I guess in its simplest, surface water is any ponding, flowing, or emerging of water occurring above the ground surface. but of course it's linked to groundwater, everything's interlinked. It might be a constant naturally occurring feature, such as a river or a lake. It might occur regularly and be water present all the time, something like a SuDS pond, which fills depending on the scale of a storm event. It might also occur infrequently in other places, at a geological horizon, possibly forming a spring, something like that. Surface water flooding linked to issues of poor drainage, blockages by debris and sewer flooding over top, or even a burst pipe. It all becomes surface water. So these processes, may become more frequent with climate change. So the map on the left there gives you an insight into the coverage of the surface water features across Shropshire. The map on the right-hand side, I wanted to sort of provide the SuDS infiltration suitability map in here, as I think part of this talk is about modelling, but it's not just about defining flood risks. It can also be about defining potential solutions. The SuDS infiltration potential map there. Very good tool to identify key areas which might be suitable for SuDS to infiltrate runoff to ground, to slow or even to stop the flow to reduce flood risk. So next slide, please. So how does surface water occur? So there's two key types of surface water flow, really. So sort of Hortonian overland flow, or we also call it infiltration excess overland flow. So basically where the rainfall is greater than the infiltration capacity. For example, if a soil surface can infiltrate, let's say, 30 millimeters per hour, but the precipitation is 40 millimeters an hour, surface flows will begin to occur. This could also be affected seasonally as well. So in times of drought and in times of the coldest temperatures, I guess the ground could become more impermeable and more susceptible to runoff. The other is saturated overland flow, which occurs as a result of prolonged periods of steady rainfall and the water table reaching the surface, where no additional water can be infiltrated. So let's go to the next slide. So how can we understand where it might occur? So we can rely on gauge data. There are quite a few watercourses with gauges, historic photos and rack marks, anecdotal evidence from people who have experienced these events from occurring. And we can use that to calibrate and validate model extents to the historic events. There's a wide range of modelling techniques available to understand the potential for a surface water event and understand where the flow routes go. So this slide shows some modelling undertaken in Pontesbury by WSP, southwest Shrewsbury, as part of a Section 19 study to come up with some cost-effective flood alleviation measures. So the detailed modelling, modelled the river and then modelled the flow routes out in floodplain. It's not just about creating a very detailed model, but it can also include sort of a halfway house using GIS software to represent flow accumulations based on LiDAR ground elevation data. So not necessarily working out the hydrological elements of it, but just running the preferential flow routes through a GIS software. So next slide, please. So what are the standard modelling techniques used for rivers in Shropshire? Well, they vary considerably, but the majority are sort of a 1D, 2D linked model. So the 1D represents the cross sections in the channel. That then talks to the 2D domain, which is represented by a grid. There's several parameters that you can change to affect flow routes into the floodplain. And each of the grids is represented by these individual points. So the ZC point up in the top right corner there defines when a cell becomes wet and dry in a two-flow model. The ZU and ZV points control how water is conveyed from one cell to another. And the HX lines, the pink lines there, show how the river talks to the. So most models tend to work in a similar way to this. So next slide, please. So the Environment Agency's risk of flooding from surface water maps use the JFlow Plus software, which is sort of a 2D mesh used to model flow routes. It provides the best national coverage really and is pretty accurate. Where we have more accurate survey data, we can use modelling software such as InfoWorks, things like that. So the figure below there shows some InfoWorks modelling, where the sewer network is linked to the floodplain, and water emerges from the manholes to represent what happens in the floodplain in terms of flow routes and flood depths. So next slide, please. So surface water flooding in Shropshire. So there's a really wide amount of data available to try and understand this. The Shropshire Council have got local flood risk management strategies, strategic flood risk assessments, and the communities at risk data set that is really, really useful to identify key communities at risk. We've undertaken our own quickfire assessment using the EA's river and surface water flood maps, and also the unique property reference number. So the data set, which is freely available, just to run some stats really. So you can see here, sort of in a 1 in 30 year storm event, there could be up to sort of anywhere between 2 to 3 across Shropshire. It could be an additional 5,000 additional properties affected if a 1 in 100 year storm event were to occur. But if we sort of look at the right hand map there and use the maximum impacts of climate change, we might be able to see what would happen in terms of properties affected by flooding from rivers and surface water directly. And the numbers go up to around about sort of 13 to 14,000 properties, with water covering around 2% of the land area. So next slide, please. Just a couple more slides on mitigation and measures we could install. So we can use the data to identify key areas at risk. There's been some really good flood defence schemes. The Much Wenlock Flood Alleviation Scheme, completed in 2018, designed to attenuate flows in a 1 in 30 year event, and reducing flood risk to around about 171 properties, and public open space and in enhancing an existing SSSI. So it's more natural schemes, that I guess the better, and more of these schemes need to be implemented over the next few years. If we could go to the next slide. I guess the Much Wenlock scheme is quite expensive. Can we do more in terms of educating people who are in the wider floodplain, encouraging the use of property level protection measures, which can be slightly cheaper and more cost effective in the long term. So the next slide, if we can. So the last slide is about sustainable drainage schemes. So SuDS are really, really relevant, mainly in these sort of, I guess, the upland areas where holding on to the water and slowing the flow is vital, in making sure that we at least aren't increasing flooding risks to downstream communities, but where possible, sort of reducing the volume of runoff. Predominantly, you can get a SuDS in a new development, but they're sort of less likely to be used as sort of retrofit schemes. But why not really? Why aren't we retrofitting more schemes? Aren't we wider SuDS schemes like the Much Wenlock Flood Alleviation Scheme to reduce flood risk in the wider area? So in terms of modelling used in Shropshire, most new development will need to undertake modelling using micro drainage or similar to model the pipe network, and then to design the overall SuDS scheme to deal with runoff over the next 100 years, including allowance for climate change. So in summary, there's some key modelling methods being used across Shropshire to understand the risks of flooding, solutions to alleviate flooding, but also I think to design new developments really to adapt to climate change over their lifetime. So thank you very much for listening, and please feel free to contact me if you have any questions.
Okay, super. Thank you ever so much, Mike, for giving us insight into surface water, flood risk management and SuDS in Shropshire. Okay, next we have Luke Neal from Shropshire Wildlife Trust. Luke's the Deputy Manager of the River Teams at Shropshire Wildlife Trust. He coordinates a range of river and water-based projects. Until recently, Luke's been one half of the Secretariat, which supports the work of the National Catchment-Based Approach Support Group. And today, Luke will talk about natural flood management in the Corve Dale and slow the flow. So it's over to you, Luke. And if we could try and keep to 5 minutes, that would be brilliant. Thank you ever so much.
Thanks, Juliana. Hi, everybody. I hope you can hear me all right and everything. Good. Yeah, my name's Luke Neal. I'm the Deputy Manager at the Shropshire Wildlife Trust in the Rivers Department. I've spent the last sort of 4 or 5 years working on Shropshire Slow the Flow in the Corve Dale. So I'm very much the low-tech person, I think, at this event, because really my job involves getting some of these natural flood management interventions in on the ground. So I'm just going to try in quite a practical way to lead you through some of that. Could I have the next slide, please? So catchment-based approach, it should be sort of bread and butter really to everybody here, is very much about taking that whole catchment approach, understanding how it all fits together. And the important point I want to mention is that natural flood management does not replace the other sort of traditional ways of controlling water and looking at flooding, but should be part of the jigsaw that complements and adds to reducing the pressure on existing systems. Next slide, please. We've been talking an awful lot about data, and I find data absolutely wonderful tool, so I use it really as a practitioner. I've put a link to the catchment-based approach data package in the chat earlier in the event, and it's something that I use to help me plan my work and understand the catchment as far as is possible. And then the slide here shows the SciMap package, which is free to use. Durham University developed it, and it shows me the flow pathways that are happening on the land. So when I'm trying to make cost-benefit decisions about where best to apply some of these measures, I find that these sorts of tools are really, really useful to help me focus my attention. That said, there are a lot of constraints in the landscape, and so the data can only really take me so far, and there's never any substitute for getting out on the ground and actually walking it and then understanding and having sort of collaborative conversations with farmers, landowners, and the people who are going to be affected to apply these things. So next slide, please. So what we're doing is we're working with natural processes. We are, you know, this is sort of all the different tools that we've got, like woodlands, riparian management, soil infiltration, soil management, all of those sorts of things are all the natural processes that we can work with. So it's a big toolkit. If you press again, please. So, and it's all about this slowing the rate of the rainwater. So what does that really begin to mean? So if you do the next slide, please. So essentially what I've got in my toolkit is a whole really wide range of different things that I can employ in different parts of the catchment, depending on slope, topography, land use, and often as not, just what the individual landowner would prefer to have on their ground, and what they see as sort of being most relevant and suitable. But there's a huge amount of things that we can employ and we can use, and in a way that we sort of build up these small interventions, we begin to extrapolate out a bigger effect. So what some of these things begin to look like then, and we'll whiz through some of these. So if you do the next slide, please, Kat. So in the Corve Dale now, we've got over 400 leaky woody barriers that are log jams. Essentially, there is design. They're not just logs thrown into watercourses. They have to maintain fish passage. They want to be leaky. They don't want to build up too much material upstream. And we want to make sure that they're going to be there for a reasonable amount of time as we restart some of those natural processes in the rivers. Next slide, please, Kat. Where there's opportunity to do so, swales can be a really useful kind of feature, and this is one that I've put alongside a track where a farmer already had a sort of 8-metre wide buffer strip alongside an arable field, and this one is combined with an earth bund alongside the track and then drainage that goes underneath, and that's taken water away from his track, and it's also now actually preventing, in some severe storm events, they had potatoes washing down the valley and actually into a property, and so this captures an awful lot of that stuff if it happens again on this land. Next slide, please, Kat. Ponds are really useful and important, and they can sort of have they're really nice because they have a much more measurable sort of effect in terms of the water that we're able to hold back. We're also, in habitat terms, we're able to restore or reinstate ponds that are in the landscape already, and generally these are items that are not sort of taking any land out of production. Do the next slide, please, Kat. So, you know, sometimes you get the opportunity. Woodlands are absolutely fantastic. We know that some of the work in Pontbrenne, that woodlands intercept and infiltrate water to a much higher degree than just fields and other systems, and actually conifer woodlands more so than broadleaves. So we've created these sort of timber bunds on the woodland floor, very cheap and easy to install. Next slide, please. I'm going to race through the last couple. Hedgerows, cross-contour hedgerows, we've put in a couple of kilometres of those. Next slide. And then also tree planting is really relevant, but often for us it's about finding those small patches rather than large woodlands that can be planted, and they can be really relevant, but they're much harder to find and to install. And then if we just flip through the last couple, so we've got seepage barriers, which are like a leaky woody barrier, but really a bit more formal and in a ditch. And then, yeah, we've got aeration, which is a really nice win-win for landowners and for us, because there's real benefits to the field system. So just click the next slide very quickly. That just gives you an idea of how the cumulative effect builds up, and a number of very small interventions begins to grow into a landscape scale intervention. Just very briefly with the next slide, I would just mention that we have been getting our monitoring and our data gathering, and we've been working with Cardiff University, who are beginning to produce a number of papers to really understand and get into the guts of what the measurable impact is, and hopefully leading to improve some of the data modelling that we'll be able to do. And I can stop there.
Super. Thank you ever so much, Luke. And thank you for introducing us to the work you've done at Corve Dale in Shropshire. Great introduction. Thank you. Okay, next up we have Susie Roy. Susie is an Associate Director at Wood Group UK. She's got 25 years of experience in academic, regulatory and also consultancy roles. In particular, Susie's worked on large-scale diffuse pollution projects around groundwater, river basins, associated ecosystems from urban sources. And today, Susie's going to provide a brief introduction to diffuse and pore source pollution from nutrients in the water environment. So it's over to you, Susie, please. And if you could also keep to 5 minutes, that would be super. Thank you. If you've got your mic on mute, Susie. On mute. You're on mute, Susie. I don't know if you can hear me.
Yes, sorry. In my excitement to talk to you all, I managed to close the tab and drop out of the meeting completely. So apologies. I presume, Juliana, you've introduced me already. Okay, so I'll crack on. Hi, everybody. If you could move to the next slide, please. Kat, thanks. So I'm just going to give a quick talk on nutrient pollution of the water environment. It's a huge topic to cover, so it was quite difficult to kind of focus down into a 5-minute slot. But I brought it down to the two main strands of, I suppose, of issues that have been raised in terms of nutrient pollution from work that's been done over the past 10, 20 years on Water Framework Directive status assessment. So the first one, and what's generally known as well, is that excess phosphorus and nitrogen lead to eutrophication in the water environment, so in rivers and lakes and in transitional and coastal water, so estuaries, and that leads to ecological damage of habitats, sensitive habitats and protected areas, so SACs and SPAs and SSSIs, Ramsar sites that we value as society, but also restricts human use of those environments in various different ways. And the second mainstream in terms of what I'm going to talk about today is nitrate in groundwater, which is it's been identified as one of the main causes of poor groundwater status in the UK and across the EU as well. And I think nitrate trends in groundwater, rising trends in nitrate, are quite well known within the water community as a key problem for groundwater. So if you want to go on to the next slide, please, Kat. One of the things I thought at this point would be really useful to do would be to step back for a second and just think about how we as society interact with water. What do we use it for? What benefits do we gain from it? And how do we value the water environment? So obviously we need water for drinking. We can't survive without drinking water. We use it for washing, for food preparation, for flushing toilets. But then we also, society, produce waste in terms of sewage, in terms of, and that also it goes with biosolids from that sewage processing, landfill, so solid waste, urban runoff. We need to grow food to feed ourselves, and agriculture requires fertilizers to help food crop efficiency increase and sort of crop yield, and agriculture needs water, and agriculture also produces animal waste as well under ammonia emissions. And we also need energy, so our vehicles, combustion engines, or burning fuels for energy production produces nitrous oxides, and that in itself, air pollution, can interact with the water environment as well to produce or to add nutrients or nitrogen to water. So we gain benefit from the water environment through all those things. We also produce waste products that then interact with the water environment. And I suppose the question is, how much are we willing to kind of step back from producing all of those waste products to kind of, how do we change attitudes? And that comes down, I think, to a change perhaps over the past 10, 15 years in thinking about how we value water. So this points to what people have been speaking about before about ecosystems. How do we value the water, a healthy water ecosystem, and what it supports in terms of society or such as tourism, fishing, seafood, recreational uses of watercourses and lakes and estuaries, but also other things that people have been talking about today. So natural flood retention of perhaps wetlands that function well, carbon capture when we're thinking about improvement of soils, and obviously water availability. So that was just a kind of, let's take a step back and think about how we value water. Do you want to go to the next slide, please, Kat? So I think sometimes for these talks you can always just get it feels like it's a really bad news story, and it feels like, oh, we've got all this pollution, all these bad things happening, but what are we actually doing about it? Well, there's actually 30 years worth or more of legislation, a whole stack of legislation that protects the water environment against nutrient pollution. There's a couple of, that list isn't exhaustive. There's also Marine Strategy Directive, there's air quality directives that are in UK law, and those pieces of legislation, especially the Urban Wastewater Treatment Directive, have seen really great improvements in terms of river water quality. So the reduction in the amount of nutrients going into rivers from wastewater treatment works has shown a real improvement in terms of surface water quality. And one of the great pieces of legislation, the Water Framework Directive that everyone's very familiar with, has really driven that understanding, or that holistic understanding, of the nutrient issue. And in the UK, I think, so Luke's mentioned CABA, and that implementation of a catchment-based approach, bringing together stakeholders within the catchments, people who are interested and impacted and use the water environment to help drive improvements and management, sustainable management of the water environment, has been quite successful, I would say, especially around data sharing and driving change. But on the other side of it, there's also the enforcement of the regulations that go with these pieces of legislation. So, for example, around Nitrates Directive and nitrate vulnerable zones, of which there's quite a big area in Shropshire. Enforcement's key, but sometimes that enforcement might be confounded by external forces. So, for example, if the market's there for cheaper food, then perhaps the environmental protection goes a bit by the wayside. So I was going to just go on to 2 quick case studies on work that we've done, not in Shropshire, unfortunately, sorry about that, but you know, it's always good to look elsewhere, isn't it, to see examples of what can be done. So the first one I'm going to talk about is a case study that we did, or work that we did, a collaborative project we did between the Environment Agency and 2 water companies in the south of England. Do you want to go to the next slide? So this is a case study that's published on the CABA website. So it demonstrates the interlinkages between groundwater, which in the chalk aquifer has rising trends of nitrate, and that groundwater then feeds high base flow rivers such as the Tess and the Itchen rivers. So the chalk streams then have high nitrate in them, which then feeds to estuaries, which then nitrate is a rate limiting nutrient, and so you get overproduction of algal mats, which means there's a damage to tourism because the aesthetics aren't great, and also to the habitats there as well. So there's this problem for drinking water, but also for habitats in this area. So if you go to the next slide, the project looked at taking all the data sets available at the 4 organisations, so it was for the South Downs National Park Authority as well, were willing to share between them in terms of land use, in terms of groundwater models that Alastair's talked about that were set up for this area as well, and in terms of understanding what the water companies were going to do in terms of working with farmers to help reduce nitrate concentrations. So we did a whole set of modelling both at the aquifer and groundwater catchment scale to understand what they could do and what measures they could put in place and what the cost would be to help drive down nitrate trends. So if you move to the next slide, I think I'd be remiss, and I know I'm a bit over time, it'd be remiss of me if I didn't mention nutrient neutrality, which is all about trying to protect, as my understanding, trying to protect SSIs, spars and sacs and Natura 2K sites from further damage from nutrient pollution, so from phosphorus and nitrogen. Water companies have got a responsibility through their Water Industry and National Environment Programme to help to understand what impact their assets are having, so their wastewater treatment works. And nutrient management plans have been produced for different catchments to sensitive sites, and Natural England has produced guidance for housing developers such that the developments must be demonstrated to be nutrient neutral. So additional population growth must be shown to go through the planning process, must be shown to not have an extra load on these sensitive areas. So if you go to the next slide, I can probably whip through this dead quick. I just thought it would be interesting to show a project where we've done an evaluation of the measures that have been put in place to offset phosphorus in a catchment, where we were using various tools that are available to understand measures that are taken, the impact or the amount of phosphorus offset there was from measures that have been put in place for farmers in the catchment, and also looking at sediment runoff, so understanding controlling of sediment runoff from tracks and roads, and an assessment of river restoration as well, to come together to understand the offset of phosphorus for this particular client who wanted to negotiate or wanted planning permission from Natural England to put in place development. So if you go to the next slide, this is the final one, I think. So we'd also thought about what they could do, propose measures of land reversion, because that's another another way of reducing nutrient runoff in terms of use of low input land use or woodland planting, riparian planting, woodland planting, or wetlands as well. So I'm quite over, so I'll come to an end there.
Okay, thank you so much, Susie, for sharing your case study with us today. It's really appreciated. Okay, next up, our final speaker for our quickfire presentations is Simon. Simon Burgess is from University Centre Reaseheath, and Simon's the head of projects, research and innovation there. He's responsible for developing and delivering various research and innovation projects across the college and beyond the college. Today, Simon's going to provide an overview of a low-cost smart turbidity sensor, which is being trialled in the Rea Catchment here in Shrewsbury this month. So over to you, Simon, and please may you keep to 5 minutes.
I'll do my very best. Good afternoon, everybody. I feel a bit of a fraud in the company today in that my expertise is not in water, but I have been involved in managing both 2 WEG projects. Next slide, please. So just so that you know, Reaseheath College, we're based just outside of Nantwich. We're a specialist land-based technical college offering apprenticeships, further education, higher education. We've got about 4,500 students on site. We offer a whole variety of courses related to the agricultural sector, land-based sector. We've got a 320-hectare farm, including a 220-head dairy herd. The River Weaver flows through some of our land. And for the last 3 years, we've been a delivery partner with University Centre Shrewsbury, University of Chester and Birmingham University in CREST. So the smart, next slide please, Kat. So the smart catchment concept uses a network of low-cost sensors that are distributed throughout a catchment, coupled with open source data and local information. I said that I had very limited expertise in the water sector, but I do have quite a lot of expertise in the energy sector, where we've done a lot of work with smart grids, and this is analogous to a smart grid. Because when you deploy sensors, you're then able to understand how a network is operating. So this, these low-cost sensors allow us to create a data-rich, real-time and interactive view of a catchment, and that's what I've been calling a smart catchment. And a smart catchment in and of itself enables us to model and optimize interventions that can reduce diffuse pollution, optimize the location of slow the flow, and facilitate the introduction of natural flood management measures and interventions. Once these interventions are deployed, we can then monitor, validate, and value those interventions. It seems to me that a lot of the problems that we have are that we deploy interventions, but the evidence base that these are working is quite limited. And so this is an attempt to try and improve the evidence base that we create. If we have that evidence base, then we can develop financial incentives, rewards, and perhaps even penalties so that ecosystem services are better delivered. And this might be through, for example, ELMS, the new environmental land management scheme that is going to be introduced in coming years. Next slide, please, Kat. So this low-cost turbidity sensor, we were asked by United Utilities to look at turbidity within a particular catchment, and the cost of the sondes that were going to be used was quite prohibitive, and the functionalities that we were looking for were quite limited. So we worked with a technology partner, FreeUp Limited, to create this autonomous low-cost turbidity sensor. And as a sensor, it measures in real time or near real time turbidity and transmits that data to a cloud-based platform. And on this platform, we've created a dashboard from that, which displays real-time or near real-time turbidity maps of the water body or catchment, and allows overlays with other open source data. So Steve mentioned a lot of the data and the data sources that are available. So we're overlaying that turbidity map with other open source data. And the dashboard that we're creating is accessible via any device with an internet connection and web browser. Next slide, please. So they typically, a sonde will cost between £1,500 and anything up to £4,000 and even above. I'm pleased to say that the sensor that we've developed is but a small fraction of this. in order to work, it requires GSM signals and bankside access, and a minimum, at the moment, minimum depth of water, and it's got to be flowing water, of 30 centimeters. We measure turbidity via two sensors, one in a range of 1 to 100 NTUs, and the second in a range of 1 to 1,000 NTUs, and both offer an accuracy of plus or minus 2%. We have the ability to read data in continuous time, every 10 seconds or so, but for the projects that we're deploying at the moment, we're doing 15-minute data reads. And with 15-minute data reads, we're able to achieve a battery life of about 6 months. And for the future, we're planning to build in other functionalities to the sensors, which will include the color of water, as well as turbidity, and then the flow rate, and then by proxy, if we understand what the turbidity is, then we might well be able to have an understanding of what phosphorus levels are, but we can also introduce low-cost sensors that will help us measure pH and BOD. And in the fullness of time, when alerts are triggered because of predetermined limits have been exceeded, then the sensor will be able to capture a sample of water, so in real time, so that can be collected perhaps through a citizen science or a river warden or a member of the EA, so that rather than waiting several hours for a pollution event or other event to appear, and by the time it's inspected at source, it's disappeared, we'll be able to capture that real time sample. And then we're also looking at the ability of self-diagnosis, so that if a sensor should move out of operating parameters, then it will be able to signal that some remedial intervention or maintenance is required. Next slide, please. So we've deployed one of these sensors in the River Weaver in Nantwich. It's worked very well. And now we are looking to develop one, as Juliana said in her introduction, to the Rea Catchment. It's going to be the first such smart catchment in the UK. For those of you who don't know, Reaction is a 2-year project. It's managed by Reaseheath, and it's supported through a water environment grant project on the Rea Brook, which rises just under Montgomery at Martin Pool and enters the River Severn at Shrewsbury. So working with Seven Rivers Trust, Seven Rivers Ecology, and Reaseheath, we're deploying 15 of these sensors at strategic locations in the catchment. Most are in the main channel, above and below the tributaries, but we're also monitoring some of the 2 of the tributaries themselves. Monitoring data is going to be collected over a period of 6 months, and the data reads are going to be every 15 minutes. And the dashboard will be created so that stakeholders and members of the public will be able to access. And the purpose of the project is to try and identify priority areas where interventions can be deployed to reduce diffuse pollution. Next slide, please, Cap. So this is a map of the catchment. You can see the main channel, and then where we've got tributaries entering main channel, we're adding additional sensors. So that's the location of the 15 sensors in the Rea Catchment. Next slide, please, Cap. And then for the future, so the Rea Catchment is going to be the first, but we're working with a water company to develop and deploy quite a large number of sensors in a catchment whose headwaters are in the Peak District, and those headwaters feed into for water abstraction for drinking water. We're deploying sensors in the River Weaver in Nantwich. So coupled with citizen science, we're going to be monitoring for NP, pH, BOD, and microplastics. The sensors in themselves don't pick up microplastics, but the citizen science will be part of that. And then we're looking to deploy in quite a complex catchment in Cheshire, a series of sensors to look at supporting drinking water abstraction. And I think that's my final slide. Thank you.
Super.
Anybody, that's my contact details. Thank you very much.
Super.